Okay, so welcome everybody to the online seminar series, Machine Learning Needs Mathematical Optimization. We have the pleasure today to have Andrea Lodi. He's Andrew and Antish professor at the Jacobs Technion Cornell Institute at Cornell University. He has a PhD in system engineering from 2000 from the University of Bologna, and after becoming, walking through the whole academic ladder and becoming full professor there, he moved to Canada, and he took the excellent research chair in data science for real-time decision-making at the Polytechnique from Montreal. And he's now at Cornell University. He has also been a consultant for the Simplex R&D team at IBM. He has received numerous prizes from the community, and the latest one, as far as I'm aware of, is the Farkas Award for his contributions to the field of optimization. So that basically tells you, that we are having today the pleasure of having a leading academic in the area of combinatorial optimization and linear programming, and that he has done extensive work in different applications, energy transport, health, production, etc., but also within the field of machine learning, and we are extremely happy to have you here. I'm not going to count your number of publications. I'm not going to count your many other things, because that would be, as we all know, you are a leading expert in the field, and we are extremely happy that you found the time today to come and talk to us. Thank you very much. Andrea, you have, say, 45 minutes, 50 minutes, take your time, and then at the end we will have the questions.
So first of all, thank you very much for the nice invitation and the nice presentation. It's a pleasure to be a kind of here, whatever that means, in these conditions. And again, so I hope to be able to meet many of you in person relatively soon. Things are moving in the, I would say, in the right direction. So what I will talk about today is my most recent work on let's say, try to look at heuristics for mixed integer optimization through a machine learning lens. And this is the outline of my talk. So I will try to convince you that primal heuristics play a central role in exact solvers for mixed integer programming. And essentially for two main reasons. So the first one is that, of course, on the one end, having a primal solutions helps speeding up the branch and bound framework, and on the one because of fathoming nodes, and on the other side, so the idea is that if you don't have enough time for essentially solving your problem, but you have to put a time limit or let's say a resource limit, then finding the solution as quick as possible leads to the fact that you are able to deliver especially in applications, a solution that is actually good enough for practical purposes. So I will speak about two topics that are around the use of machine learning for heuristics in MIP, and one is learning to schedule heuristics in MIP, and especially in SCIP. And the second one is we're gonna revisit the local branching framework that Matteo Fischetti, that is in the audience as far as I know, and myself have devised a long time ago, 20 years ago, and looking at it by a machine learning perspective. So the first part is joint work with some of my colleagues at both the University of Toronto, so Elias Khalil, and at ZIB in Berlin, so Antonia Miela is, I think, in the audience. I see her passing, her name passing. Ambros Gleisner and Sebastian Pukut are the other co-authors. So this is the link to our, or at least the information on our technical report in the archive that is going to be appearing in RIPS 2021. So the idea, the basis of what I presented today about this is the fact that in MIP solvers there are many heuristics that are being devised, and somehow the idea is that we wanted to find the best possible way of using those heuristics within the solver in order to, as I said before, speed up the computation as much as possible. So let me remind you the context. So we're talking about minimizing a linear function over a set of linear constraints, the binary variables, for the purpose of this talk, but we can extend this to, definitely it's not the requirement, but for the, let's say, for simplicity here, we're talking about binary variables, and what we have, I'm reminding you the framework that we are, the branch and bound framework that is implemented by all the solvers. So the first the first idea is that you have two trajectories that are leading to the that have to essentially to touch each other in order to prove optimality and essentially solving the instance that you have. The upper trajectory, the red one in the picture, is the primal trajectory. So you want to compute solutions which are as good, as quick as possible are good, and the dual bound has to, so essentially means that we have to making it going down. The value, we start by a higher value and then you're going down, until this trajectory, the red trajectory, encounters the blue trajectory here in the picture, which is the one of the dual bound that we are increasing over time. So essentially, this is when the two trajectories, let's say, get together, then what we have is that we have a proof of optimality. So this is obtained by, of course, by analyzing a branch and bound tree. So a tree in which at every node we relax the integrality requirement, we solve a relaxation, and we essentially constrain the relaxation by branching on the variables, by adding cutting planes, by do a bunch of different things. So what we want to obtain is indeed, starting by the value of the LP relaxation, we want to get the gap, which is the difference between the primal solution and the dual solution, the best primal and the best dual solution at any point in time. We want this gap to be decreased as much as possible, and this is better primal bounds. We have more nodes which are pruned, and the gap is closed faster. And on the other end, as we said before, better feasible solutions early, more effective decision making, because if I stop at any point in time, then what I get is that I get essentially a good solution to be delivered for application purposes. So now, the one good way of measuring the quality of heuristics within a branch and bound framework is the so-called primal integral. So the idea, the primal integral is the area below the trajectory, from the optimum below the trajectory that is the primal, the red trajectory in the previous slide. So if you are able to compute the optimal solution immediately, then essentially the error will be zero. And maybe it will take some time to prove optimality, but at the same time, you have already, if you stop at any point in time, then the solution is already there. On the other hand, if the solution is obtained at a very late in the process, then the quality of what you're offering to the user may be not particularly satisfactory. So if we reduce the primal integral as much as possible, then we win in this particular game. So now we will use over this talk one problem that is actually difficult for the primal perspective, which is to call it the generalized independent set problem. In this problem, we have a graph, an undirected graph, and we want to select a subset of the vertices to maximize the revenue. And we need to pay a cost for selecting adjacent vertices. So the idea is that you have essentially the two parts in the objective function. One part on the left is the revenue that I can get by selecting the vertices, and on the right hand side, on the negative side, so on the blue here in the picture, we have that if we are selecting two vertices which are connected by an edge in the graph, then we have to actually pay a penalty associated. So this problem is difficult in the sense that if you, so the generalized independent set problem is challenging from the primal perspective because of this picture. You can see the blue trajectory, and this blue trajectory shows you that after 4 hours, for example, in this instance, which is not particularly big, you are not able to actually converge to optimality, but at the same time, which is even worse, you are essentially 10,000 seconds here, but you are also have a significant primal gap, but also a significant, essentially, how could I say, a significant primal integral, because is the curve below, is the area below the curve, the trajectory of the blue trajectory here in the picture. So we would like to do something to improve this, and our idea is to do it in a solver in a context, an environment that we know well, and which is SCIP. And SCIP is, as we all know, is one of the fastest non-commercial solvers for MIP, and it's a very complicated object. And we will do some implementation also using a library that is called a call, or an environment in which you can do essentially try machine learning ideas in the and connecting them to indeed MIP solving. So SCIP, this is a nice picture showing how many primal heuristics there are within SCIP. So all this yellow, let's say, dots over there are all the primal heuristics that you can use in SCIP. And in particular, we will concentrate on two types of primal heuristics: the diving heuristics. So diving heuristics are essentially all those heuristics that are actually doing some sort of say fixing of the variables with some recomputation and fixing of the variables of a node. When you solve the LP relaxation, then you can round the variables and try to see you can recover a feasible solution. Then this goes to a really rounding completely the solution to iterative rounding, in which you round some of the variables, recompute the LP, and so on and so forth. There are 15 diving variants in SCIP, and those diving variants have different rules for fixing the next variable, for round the least fractional variable, fix variables in dense constraints, many different things. And they are one important parameter is the maximum number of iterations, so the max diving depth that actually the heuristic is using. So the idea here is that we want to manage heuristics. So SCIP implements 57 heuristics, different heuristics, and some of them are effective on a particular node, on a particular problem, on a particular context, and some of them are essentially failing. So what does it mean, fail? Essentially means that they are not able to, they are run, but they are not able to find a feasible solution. So this is going to be, in a certain sense, every time that the heuristic is improving the solution, you have something good, because the primal integral and the primal gap are actually diminished. But if the heuristic is failing, essentially you're left with nothing, in the sense that you have invested some computing time, but nothing has happened. So there are also and the managing heuristics means two things, especially at the same time. Not every heuristic has the same complexity, so in the sense of heaviness how heavy it is in terms of the computation, so how much resources, time, essentially, it takes. And it may lead to a different situation in which you want to use heuristics in different forms. So with depending on the problem that you're solving, you want to use them more or less, or every one of the heuristic has to have some sort of different characteristics. So for example, the heuristic loop is the following. For each heuristic, in a certain order of priority, for at most max number of iterations, so that is actually associated with the specific heuristic, you perform one more step, which means that you give some additional resources to the heuristic until a new incumbent is found and the loop is interrupted. Okay, so the idea is that there are two main important parameters that you have to play with. One is the order in which you are running the heuristics, and the other one is the maximum amount of resources that you are allowing to each one of those heuristics. So, of course, these are two parameters. So the first thing that comes to mind is that you can do some sort of parameter tuning. And in this parameter tuning, you can essentially use some automated configuration for mixed integer programming solvers, which have been an active area of research since the beginning of 2010. There's a nice seminal work by Hutter, Oss, and Leighton Brown. Of course, this is actually one possibility, but this possibility is somehow has limitations. So one thing is that you have to do black box optimization, which can be slow. And for our MIPS, each evaluation may take hours because essentially you have to collect a lot of data that is going to be difficult and time consuming to collect. And in particular, it doesn't not exploit the fine-grained information about how parameters alter the solver behavior. So we would like to go a little bit deeper into the order of the parameters and the way in which the evolution of the branch and bound itself. So just to convince you that these two parameters are very important, let me show you this picture. So this is actually two different classes of problems. So one is the generalized independence problem that I already introduced, and the other one is fixed charge multi-commodity network flow. Blue, the GISP, and the network, the multi-commodity flow is actually in yellow here. And as you can see, these are two different heuristics, and the solution, this is success rate that they are having. So this means that depending on the heuristic, the success rate can be very different. So each one of the bars of the pairs of bars is a heuristic, and as you can see, for example, the first one is very good for both GISP and multi-commodity network flow. But for example, if I look at the fourth or fifth, it's very good for network flow, but it's actually not particularly effective for GISP. So essentially, this means that if I depending on the class of problems that I'm trying to solve and I'm trying to schedule heuristics for, then the order in which I run the heuristic can have a significant impact. On the other hand, also the maximum number of iteration matters. So you can see three different evolution of heuristics here in terms of percentage of solution found. As you can see that this depends on the number of iterations in a very different way. So the green heuristic that you can see at the beginning is finding solutions very quickly, but then in the first, let's say, 100 iterations, and after that, there is nothing more that can be added. Different is the yellow one, and even different is the blue one in the evolution over the number of iterations. So essentially, this tells us that there are some heuristics that should be run with a limited number of iterations, because after a certain amount of iterations, they will very rarely converge to find the feasible solutions. So now, putting all this together, so there are MIP is challenging on the primal side. So you would like to actually improve the work of the MIP solvers in finding feasible solutions. The distribution over the instance may change quite a lot the situation, depending on, for example, the order in which you want to run the heuristics, of how many iterations you want to run them. There are long solver times, which I mean somehow makes complicated the situation in terms of running let's say, black box optimization in order to do parameter tuning. And finally, we would like to have something, I mean, that is not a heuristic that is developed for a particular problem every time, but we want to have something that is used in general for SCIP. So in order to do that, of course, a natural idea is to try to use machine learning, so which means collecting data and, in a certain sense, try to find the good compromise between these situations. And then it's easy to see here that in this these are three different nodes performance, and this is the number of iterations, so or specific iterations that for three different heuristics. The heuristics are indicated with a different color, and the nodes are so 3 for each one of the 3 nodes. And these are 3 different nodes in the branch and bound framework. And then the question is, how do I need to schedule heuristics in this case? And the best situation for us is something like this. So the yellow heuristic is the one that I would like to run first for limited number of iterations, 1 iteration only, because if it finds the solution, it finds it immediately. After that, there is nothing to do. And then the second heuristic is the one that we want to run for 3 iterations, because it will actually not be paying anything for the first node, because already the first one has found the feasible solution. And you recall that once one of the heuristics finds a feasible solution, and then we stop, the entire loop is stopped. And after 3 iterations, there is guarantee that this is actually going to find a feasible solution both for node 2 and node 3. So this is actually, in this particular case, the optimal schedule that we want to apply. And we were going to find a feasible solution for the 3 different nodes. Now, how do I do this computation? So I'm collecting data, and then I'm doing training, and particularly I run the solver on training instances. Then I execute the heuristics very aggressively, collecting performance data. We will see in a second what to do. We combine the data and we solve the scheduling problem. So the scheduling problem actually can be formulated as a mixed integer quadratic optimization problem. That would be too much, let's say, time consuming to solve that problem in that form, even offline. And actually, and so we're going to do it by a greedy heuristic, which is largely inspired by the PhD thesis of Matthew Streeter. And in particular, in the implementation of the data collection part is, again, similar or inspired by the work of Elias did long ago, I mean, a few years ago in 2017, associated with the idea of, let's say, running the heuristics, the primal heuristics in a mode, let's say, hidden mode. So it means that you're running the heuristic, every one of the heuristic, and you will not, if the heuristic finds a feasible solution, you're not updating the solution itself in such a way that you can collect information of each one of the heuristic and the rate of success of each one of the heuristic. We can do parallel data collection. We have 1 solver run per instance. We solve the scheduling problem in this, which is strongly NPR'd with this greedy heuristic, and we put all this together. And at the test time, once we have done the entire, let's say, we've done the entire training offline for a class of problems, then we run, we modify SCIP in the sense of the order in which and the number of iterations that each one of the heuristic has to run, and essentially we run SCIP as it is. So we are not doing any other modification, and this is on the left-hand side of the slide. You can see the fact that there are every one of the heuristic has a different color, has a different number of iterations, which is the width of this box. And SCIP is run in this form, so there is no additional, let's say, computing time that is needed for finding the order or anything else. So now this is what we achieve in terms of, again, coming back to the generalized independent set problem. What we have is in the primal integral, I go back to that slide and then I show you that this is the trajectory of the scheduled heuristic. So in the trajectory, the yellow trajectory is showing that there is a significant improvement in the area that is below the trajectory of the heuristic, and in particular, if I go to the aggregated results, I can see that the default SCIP, I can make an improvement over 33% reduction of the time as to solution and 49% reduction over the average primal integral. These are 240 instances. We train on small ones. We test on the instances which are 3 times larger, and which means that the good news is that the machine learning approach that we are applying here generalizes well to larger instances. So this right column also tells us that a strictly better primal integral on 92% of the cases. So our framework really pays off. From a qualitative perspective, you can see the scheduled heuristic pictorially on top versus the default one. In the default one, the heuristics are run for the same number of iterations in SCIP, while as you can see that the size of the box, the width of the boxes shows that our heuristics are actually selected, the number of iterations is selected in a quite a different way, and you can also see that also the order is quite different for us. Let me wrap up things and say that by doing a comparison, so you can use a SMAC, which is a comparison to, I mean, essentially it was one of the strongest parameter tuning framework that you can use. And SMAC directly optimizes the ideal metric, which is the primal integral. While in our approach, I didn't really spend too much time, but what we are optimizing is in a certain sense, the rate of success of finding feasible solutions for the heuristics, which is of course only a proxy, because you can find feasible solutions, but maybe those solutions are not improving versus the current one. Still, SMAC barely matches our method in terms of quality of the solutions, and it takes often 2 orders of magnitude more time to do the entire computation offline. So wrapping up, we have a single comprehensive framework for managing heuristics. This can be retrained for each one of the class of instances that you want. This is extensible to, I mean, in this particular case, we applied it to in the paper to diving heuristics and to heuristics, local search heuristics. But I mean, this can be applied to arbitrary heuristics in SCIP or wherever you want. And it's quite fast to train and use at test time. Again, this is the link to the paper that we wrote about it. So let me switch to the second topic that I wanted to cover today. And this is going back to one of my, let's say, first paper or contributions to the area of, definitely the first one to the area of primal heuristics. This is a joint paper with Matteo Fischetti and published back in 2003 in Mathematical Programming. And this was the first paper essentially to propose to explore large neighborhoods directly through a MIP call, so using MIP as a black box for this. We are revisiting now the paper, and the contribution of local branching through a machine learning perspective, and this is actually joint work with Feng Liu, that is my student in Montreal, and again Matteo. with us in this enterprise. So let me remind you what local branching is about. So the idea is sketched in the right-hand side of this slide. So we are still thinking about a mixed integer linear optimization problem with binary variables. The binary variables are important for us in this particular context because we will define the so-called binary support of an initial solution. So we start with one solution, which is on top in this picture, x1 bar, and we say that we can, considering the binary support, so the variables which are set to 1 in this solution, we can add a single invalid, of course, inequality to our original MIP and say that we don't want to change too many of the decisions associated with this particular solution. So we're saying that so the first term in this in the constraint that is on the bottom of our slide says how many variables are switching from 0 to 1 in the new solution that we want to compute, while the second part of the constraint says how many variables are switching from essentially from 1 to 0. So we count the number, the Hamming distance between all possible solutions and the solution that we're starting from, so the reference solution, and we fix arbitrarily this number to k, and we say that we want to only consider solutions which are at distance maximum k from the solution that we have. So now at this point, what we have is that on the left, we are exploring the neighborhood obtained by adding this, as I said, invalid constraint by just running our favorite MIP solver on the obtained problem. And if we are lucky, we get a new but improved solution, x2 bar, and we can go to node number 3 and exploring the neighborhood now of x3 bar and continue like this. So in the meantime, if we want to keep this framework as an exact framework, we can essentially, revert the constraint that is delta of x bar less or equal than k, saying that if I explore it to optimality, the neighborhood which has been defined, then I can just revert the constraint and then say that any other solution I care about must be at least k+1 bits away from the current solution. So now this is the original framework of the local branching, and we have a slight variant in which called the symmetric form, which is the variant in which essentially we are just counting the number of binary variables which are switching from 1 to 0. This is particularly useful for the problems in which, for example, we have a fixed number of variables that are in the solution, for example, the TSP. So now, why this framework has been, let's say, somehow popular and let's say effective. The first is that there is a sort of integration between local search meta heuristics within mixed integer programming solvers, has shown for the first time that we can explore neighborhoods of a large size by just running a MIP solver as a black box, and the scheme is quite flexible. It is exact in nature, even if, of course, has been used and by ourselves first as a heuristic, in the sense that you can put a limit in the number of iterations that you are, number of nodes that you are exploring in each one of these triangles in the picture, and you can do plenty of different variations in order to converge as quick as possible to good solutions. And of course, this has also been integrated into the MIP framework by running it on specific nodes on the branch and bound. However, now looking back, there are also limitations. So the default, the first one is that the default value of k is fixed. So we did some preliminary experiments, and we ended up to say that k equal to 20 was actually a good number. And so we ran all our experiments in the paper with that value, or with 10 if there was an asymmetric form. The distributions over the instances is absolutely not taken into account. We don't do anything different for classes of instances which are different. And of course, this is also true that we not even really take into account what is the quality of the solution. We are just given an initial solution in some form, and then we go for that, and we don't adapt K to that particular solution. So now, what happens here? So it happens that you can see in the two pictures on the left is that the size of the neighborhood really matters. So the initial K, let's concentrate first on the initial K. As you can see in the top picture on the left, so this is the objective function evolution depending on the neighborhood size. So R is between 0 and 1, means R times n, the number of variables, tells us what is the size of K of the neighborhood. As you can see that for a small size neighborhood, the improvement that we can get in the objective function is very limited, starting from one solution, that is 1 in this picture, so you're going down. Of course, the smallest neighborhood, the fastest is its exploration. And as you can see, at some point, of course, you can get much better solutions, but at some point, of course, because every solution is there, so even the optimal solution is for a sufficiently large value of K, but the point is that it's going to take a lot of time to actually explore that particular neighborhood, and you cannot be effective anymore. So we are shooting for finding this sweet spot in which the neighborhood is easy to explore, so fast, but at the same time, the improvement is significant on the quality of the solution. And so we are shooting for finding this K1, sorry, that is the first K that we want to solve in let's say, in node number 2 by indeed using a particular value of K. So how do we do that? Well, of course, again, you can do black box optimization for this. So it's a performance, you define a performance function, which is the improvement, a MIP instance, a set of values for K1. And the goal is to solve this optimization problem that you can see on the left, which is K1 over this set of possible value of K. And the objective function is to find the best essentially improvement possible based on the time limit that you have and multiple things. This can be solved by black box optimization, model-free methods. You can do grid search, Bayesian optimization. The limitation will be that the function evaluation for each instance is very expensive and is not actually compatible to actually use it online. So now our idea, our suggestion is let's try to learn to predict K1 through a regression task. So we do data generation by solving a black box optimization offline. So the idea is to try grid search on many values of K, fixing a time limit at the beginning. And we do the data generation as is shown in the upper part of the picture on the right. So you do the data generation, you do training, which is again a regression over the data. And the parameterization of the model, of the machine learning model, will tell us from the regression model what is the size of the predicted K. At that particular point, once we have predicted K, we run the local branching as it is, and we actually do an evaluation, a comparison between what we are going to achieve. The regression task is easy to define. So if capital L is the loss function of the solution, f theta of I, capital I, obtained by the regression model over the optimal one, which is obtained by doing this grid search, and then we take an average, of course, over the class of instances, set of instances, and but what is the model? So what is theta here? So the model is we're using a graph neural network, so a bipartite graph, which is a bipartite graph in which we have on the left the variables and on the right the constraints, and we have a connection between a variable and a constraint if the variable is actually present in a particular constraint. So we are capturing the structure of the problem by actually using this graph neural network. Graph neural networks have been used already multiple times to solve machine learning, let's say, tasks for combinatorial optimization problems. We have a paper selecting the branching, the variable to branch on in mixed integer optimization that was published in Heuristics 2019. This was not the only time, has been used extensively in many other contexts. So does it work? Well, quite well in practice. So the implementation is in Python using SCIP, and again using a call, our environment for machine learning for discrete optimization. We have benchmark of set covering a maximum independent set. The first solution found, we have two different initialization. One, the first solution provided by SCIP, so computed by SCIP. The other one is the best solution at the end of the root node in SCIP. And we are comparing here the local branching baseline with the local branching regression. So just using regression for essentially for computing the first value for K. And as you can see, there is a significant improvement in the table 4. So the first one on the top here is the average primal integral, while the average primal gap is given in the bottom table. As you can see that in all contexts, we are able to actually improve the local branching baseline significantly by just predicting the value of K1. So after that, we switch back to the idea that that we're using a local branching exactly as was designed originally, and we continue in the same form. So this is, however, only for the first value of K, and already the local branching framework in the original paper had some sort of adaptive application of K. So depending on the fact that the heuristic, the solution of those triangles was actually effective or not, we could reduce the size of K or increasing the size of K, let's say, dependently of the success. And what we have been trying to do is to, again, connecting this to data and doing this in a Markov decision process type of approach by implementing a reinforcement learning framework. And we are, so now on the top, we have the prediction first value of K, and on the bottom, we have the evolution of the local branching, in which now there is this red box, which is on the bottom, which is the reinforcement learning approach, which is online deciding how to change the framework. Of course, again, this is connected with having a lot of data and try to train over this, and then using the policy at runtime. But as you can see, the Markov decision process idea is quite natural. We have state space with the set of solutions, the status solution of local branching heuristic. As you can see, on the top right picture, you have 4 different statuses which are optimal, so it's solving the neighborhood to optimality, infeasible, not improved into the time limit, or improved into time limit. Improved into time limit means that I'm solving the submip in time limit, I get into time limit, but I improved the solution. Not improved, I ran into time limit, but I didn't improve the solution. So the blue line here splits into submit solved and submit unsolved. So time limit has been reached. The red dotted line is splits into the objective function is improved, or the objective function is has not improved. So the action space is simple. So we essentially increase a step by a step, K step, the value of K, or we leave it as it is, we decrease it, or we reset it to the original value. And the policy pi maps a state to one of the 4 options before, while gaining a reward, which is the improvement of the objective function times the time spent in essentially exploring the neighborhood, which takes into account both perspectives, so the improvement, but at the same time, as we've shown in the original framework, the idea of how to use the time wisely. So these are some preliminary results. We have much more into both AAAI submission that is currently evaluated and in recent work. that we are finalizing in order to submit to potentially to a journal. So as you can see here, still the reinforcement learning by using some basic algorithm for learning, which is a policy gradient method, is actually able to improve quite a lot. So the LB regression enhanced by the reinforcement learning approach, so the green dotted line, is able to actually improve significantly. So you get a big improvement, of course, with respect to the lower local branching baseline, especially because we are using the regression quite a lot. And then there is a 29% also improvement over the regression model that is not using this adaptive way of changing K over time. Most of the good news here in this framework are on the fact that the generalization is surprisingly effective. So I didn't discuss this. I don't have slides because of a matter of time here, but I'm running really out of time, I think. But the idea is that essentially using a graph neural network means that this training has to be done differently for each class of instances. But we have been able, while the reinforcement learning is not trained on is not using information associated with the class of instances, but just using the evolution of the framework itself. So the signal given by the possibility of solving or not solving each instance and each, let's say, neighborhood. But the good news is that we have been able to actually train on a very heterogeneous set of instances, 0-1 instances, and it seems that the performance that we are obtaining are extremely good, which is very good news for us. So let me draw some simple and quick conclusions. I believe that the amount of opportunities for using ML into mixed integer optimization is quite high. The mean solvers are collections of algorithmic ideas, some of which are very heuristic, and this can be clearly benefiting from using data and learning quite a lot. We are only at the beginning of this road, and the challenges are many, but this looks promising to me. The challenges are mostly on the use of the right metrics in order to make sure that what we are obtaining is correct and is an improvement of what we have already. And let me just tell you that ECOL, so the framework that we have, that my team in Montreal has developed in terms of machine learning for, let's say, combinatorial optimization. So this environment in which you can implement your ideas by interfacing with SCIP, collecting data and running your, let's say, learning tasks, has been a subject of NeoRIPS 2021 competition that has, I think that the ending date was actually yesterday. So there's no time anymore for doing this, but still I think it was, I wanted to point out that this is something that is try to bridge the communities, machine learning community with the combinatorial optimization community, giving an environment in which ideas can be used and can be tried very quickly, and let's say the data can be collected and used and reused by different authors is very important. There were 3 tasks in this competition. Primal task, similar to what I described today, if you want, a dual task in terms of improving the dual bound, and configuration task was the last one. So that's it for me, and I'm happy to any questions that you have. Thank you very much for your attention.
Thank you very much, Andrea. It was very nice presentation. So for the audience, if you raise your hand, then we will give you, say, the rights to share your video and your micro. So are there any questions in the audience? Yes, so Jan, Christina is going to give you the rights, and then you can pose the question yourself.
Yeah, So thank you very much, Andrea, for the presentation. I think that the question I have is more at a high level. When you describe the data and find an embedding for a problem, how much of it is actually features about the instance you solve, and how much of it are features about the node itself and when you are in the solving process? And my second question would be, also, you're looking at specific, class of problems. So in some way, you don't need to have a good encoding of the problem instance because, you're only giving problems that have a similar structure, so to say. And so, what are your thoughts on how you could encode the structure so you could have a strategy maybe that is more agnostic to the type of problem structure you're dealing with?
Both questions are very interesting and very, of course, let's say, very punctual. So let me start by the second one. So this is about generalization. So as I try to touch it, of course, it's a big topic. So in the first problem, so in the scheduling of the heuristics, this has been really designed to, let's say, collect data and generalize to larger sizes, but not try to generalize really to different classes of problems. Because first of all, well, the effect of heuristics really depend also on the difficulty of the problem that you are solving. So essentially here, we have a situation in which, I mean, in those two classes of problems that we have taken into account, the primal solution is actually difficult to find. There are multiple classes of instances in which doing some type of work when SCIP or your favorite MIP solver is actually finding solutions very quickly, it's probably not paying off very much. The second one, in the local branching, surprisingly, as I was saying at the end, the generalization is working very, very well. So we can see that the first part, K1, the computation of K1 is can be improved by using graph neural networks and really tailoring this over the class of instances that we want to solve. But we have seen that maybe not so surprising because even k equal to 20 fixed value was working relatively well in the original paper. But what we can see is that training or a completely heterogeneous set of instances is quite effective in the sense that overall we have been obtaining very good results with a small deterioration versus let's say training on homogeneous class of instances. About the embedding, so the first part of the questions, I think part of it I already answered by the generalization thing. My impression is that the data is of course very important, so we have to take that into account very much, and still I mean that's the part that we're exploiting the most. The nodes are yeah, looking different one from the other, but if we want to go so much particularly into taking into account node by node, that will be too hard in my opinion, and will be disrupting the overall framework of SCIP. So you have to find the right compromise between saying, okay, yes, maybe there is more information related to this particular node, so we can do better, but on the other end, then they will require much more online computation, which we don't want to do it, because again, asserting how difficult it is, each one of the nodes is difficult in itself.
Thank you very much.
I hope it answered your question.
Yeah, thank you.
So, Nagisa, yeah, we are going to give you the rights. Just a second.
Hello, can you hear me?
Yes, we can hear you.
Thanks. Thanks for the presentation. I really like the topic and very exciting, I thought. My question is very simple. I was thinking about the second graph neural network thing, and I was very surprised with the fact that the training instances are very small, like namely, like we only had 200 instances for like training and evaluation and test. And I was wondering, like, is this because the like instances are small, or like a neural is small, can train with this small number?
Well, the number of instances is small, but the number of data points is large, because we actually try with every size of K at the beginning, so going from very small to very large. So we can collect a lot of data points, or even in a small number of instances. So that is, I think, is the trick that we're applying in this particular case. So it's not one instance, one run, but is one instance, many, many runs. And so this leads to the fact that we have enough data to learn, in my opinion.
It's like how large is the instance, and how much time did you spend for the training, if you remember?
Well, it's actually quite fast. The training part is a relatively fast process. Most of the training, it depends on solving those instances. And actually, I didn't say it explicitly. It's a good, thank you for the question, for giving me the possibility of saying this. So the results I presented today is with using a local branching in a for a restricted amount of time. So the idea is to integrate it into a larger, let's say, framework that is not running local branching as a standalone. So it's 1 minute, and every single iteration is up to 10 seconds. So potentially is a small number of calls. So what it takes time is collecting data, so running all these options with different sizes of K. But then once you have this data, the neural network that we are using is relatively simple, and we are not, the training is actually in the order of, let's say, 1 hour at most. So we're not really and we're not running it over a really big architectures or anything like this. It's relatively simple.
Thanks.
Thank you, Nagisa. Thank you, Andrea. Are there any other questions in the audience?
Well, feel free to reach out to me. I will be happy to discuss any one of those offline in case.
Okay. So if there are no more questions in the audience, then we would like to thank Andrea for making time today to come. And we will see you next week with another of our seminars. Thank you very much to everybody.
I see Emilio.
Bye-bye.
Bye, Emilio. Hi, everyone. Thank you so much for the invitation. Bye.
Bye.
Thank you for coming.
Ciao.
Ciao.
Bye.